From the position time graph and the velocity time graphs that you generated in the lab, you very likely produced an equation that looks somewhat like this for the position time graph. And we know as a class we got an average slope for those velocity time graphs of somewhere around 9.8. So I just want to make sure we touch base with that because that is something that every group likely found, and I want to make a connection between those. So if I can take a look at this, what I want to point out is the reason we got that average slope of about 9.8, no matter what the object was, no matter what the mass was due to the fact that every single object that is on the surface of the Earth accelerates due to gravity at about negative 9.81 meters per second squared. So that slope we were calculating, since it was the slope of a velocity time graph, that gives us the acceleration. We dropped all of these objects in a simulated environment on Earth, and all objects on Earth are going to accelerate at negative 9.81 meters per second squared. Doesn't matter if it's a heavy object, a light object, in a vacuum, I should say. In the absence of air resistance, every object on Earth will fall at about negative 9.81 meters per second squared on the surface of the Earth. All right, so that's a value that's worth memorizing. You will be given that value, but we're going to use it so much since most of our analysis will be done on Earth. And just understand that the acceleration due to gravity, it's still lowercase a to represent acceleration like we normally do. But if it's specifically the acceleration due to gravity, you will very likely see this lowercase g here pop up. So lowercase g just quite simply means the acceleration caused by gravity, and on the surface of the Earth, it's about negative 9.81. So that's why we wound up with that slope there, because all of these objects were dropped on Earth. So we were getting that acceleration due to gravity. All right, what I do want to point out here, I'd like to make this connection. So if we all look at our equation from our position time graph, we all likely wound up with some kind of equation that looked like that. If we want to know the height of the object above the ground that we're dropping, we all got somewhere around negative 4.9, negative 4.91 times time squared. Okay, so that's most of the position time formulas that were produced. And I do want to point out the fact that negative 4.905 is 1/2 of negative 9.81. It's exactly 1/2 of negative 9.81. So there is a connection there. The height above the ground was based on how quickly gravity was pulling that object down. And there's a reason why each of these graphs that we generated produced this connection here. Let's see if I can get this correct. So if I take out negative 9.81 and I replace it with little g, like we realized before, is the acceleration due to gravity, and we realized that the height is really just your change in y. What I'm really doing is I'm taking this equation. Come on, I'm taking this equation up top, and I'm just replacing it. So I'm replacing delta y as the height because that's the change in y, how high above the ground you are. And instead of 4.905, I'm just quite simply saying, well, it seems to be exactly half of that acceleration of gravity on Earth. So if you bear with me here, that is essentially the same equation we've been using this whole time. So if you take a look at one of the kinematic equations we have, delta x equals vit plus 1/2 at squared. Well, if you realize that this object was being dropped when you guys launched these in the lab, you weren't giving them an initial velocity. Well, that means this pretty much, okay, still don't know how to use the iPad, awesome. So this basically is 0, okay, and that's because it was dropped. So because those objects were dropped, they have no initial velocity. And really, they weren't going horizontally, they were going vertically, so we kind of replaced that with delta y. And we can say to ourselves, well, what was causing these to move down? Well, that was gravity that was accelerating. So if I take that kinematic equation and I just adjust it, so, well, there is no initial velocity, so that goes away. I wind up just getting 1/2 times the acceleration due to gravity times the time squared, which is exactly what I have over here. All right, it's not super important that you understand everything I just did there. I just like to show it at least once. The more important thing is I just want you to see that there is some kind of connection between kinematic equations and these values that we were getting from this lab. Okay, because what all of this means, please make sure you have this jotted down, pause the video if you need to. We are going to be looking at free fall over the next week or so, and it's important to be able to define it and understand something about it. The first thing we have to understand is that the definition of free fall any object that is moving under the sole influence of gravity. There is exactly one condition to be an object in free fall, and that is that gravity can be the only thing that's acting on you. So if you're in a plane and the plane's engines are going, that's generating thrust, that's something other than gravity. So that is not a free falling object. If the engine shut off and now the plane began to just fall out of the sky, that's a terrifying situation, but that would, in that case, technically be in free fall. So a lot of objects in sports are in free fall for most of the time. So a basketball, anytime you shoot it, pass it, anytime it's traveling through the air and no one else is touching it, and the only thing acting on it is gravity, that's an object in free fall. In baseball, as long as it's not in someone's hand or someone's mitt or being hit by the bat or on the ground, as long as it's basically moving through the air, it's in free fall because gravity is the only thing that acts on it. So make sure you understand that definition. And because, as I pointed out previously, you can analyze these using the kinematic equations, as I showed you in the previous slide, it's important to recognize you can use all 5 of these kinematic equations. The only changes you have to make, replace your acceleration variable with the acceleration due to gravity, little g. So usually 9.81, negative 9.81. If you're on Earth, if you're on the moon or Mars or Jupiter, it could be stronger or weaker, but you would know that value. But recognize the acceleration is not something you usually have to calculate. It's a known. Okay, we know the acceleration of gravity on different planets and on our own. And generally, you're going to replace delta y with delta x. So if we look at the equation down below, like we showed before, you could use that equation and just simply replace the horizontal displacement with the vertical displacement. Instead of some acceleration that you calculate, we know that it's going to be negative 9.81. So let's go through a few examples just so you guys understand how we can apply these. So again, pause the video quickly if you want to jot this example down, and then you can play it when we walk through it. So you have a rock that's being dropped from someone on top of a cliff over some water. We know that it takes about 3.5 seconds for that rock to fall all the way down and hit the water. So the question there becomes, how tall is this cliff? Now that usually throws people off right off the bat because we have one variable, we have time. That is it. So how in the world can you solve this using kinematics if you need 3 of those kinematic variables? We have to be very careful about what's going on here. So the initial velocity we actually do know. Anytime something is dropped, you have to realize it's dropped from rest. That means its initial velocity that split second when you first let go of it is actually zero. It will not be 0 if you throw it downward or you throw it upward, but anytime you drop something, its initial velocity is 0 because gravity hasn't really had enough time to grab hold of it. So we say that's 0 shortly after beginning to increase. The final velocity we do not know. Now, some people want to say, well, when it hits the water or the ground below, maybe the final velocity would be 0. Like if it hits the ground, it stops moving. If it hits the water, maybe it bobs to the top and then it's just floating there and it's 0. Guys, we're talking about free-falling objects. The second that hits the water, it's no longer in free fall, and we can't apply this. We can't analyze it as such. So the final velocity is actually unknown here. That would be the speed right before it hits the water. It's going to be moving pretty quick at that point. We don't know what that is. Well, the acceleration is actually known. If this is on Earth, we know that all objects accelerate vertically at negative 9.81 meters per second squared. We don't know what the height of the cliff is, but we know that this object fell for 3.5 seconds. All right, so we're being asked how tall is the cliff? How tall is the cliff is basically the vertical displacement. So final velocity is the one variable that I don't care about at the moment. And if I choose the one equation that does not have final velocity, that should be delta y instead of delta x, is VIT plus 1/2. I can write A, I like to write G because it's the acceleration due to gravity. But that's just our kinematic equation, just substituting in delta y instead of delta x and G instead of little a. Okay, but you can see here it's the same thing. Either one of them is acceptable, so it doesn't matter. All right, so if we plug in what we know, our initial velocity is 0. Our time was 3.5. Well, that whole thing is just going to cancel out. Plus 1/2 times negative 9.81. And my time was 3.5 seconds, and I'm going to square that. All right, if I plugged it in my calculator, we get 1/2 of negative 9.81 times 3.5 squared. I get negative 60.09 meters. Now that throws a lot of people off. They say, why is it negative? Well, we have to think about it. We're looking at this rock here, and the rock began up here and ended down here. So which way did this rock move? It moved downward. This represents the displacement of the rock. The rock is now 60.09 meters below where it started. So we just flip that around. If I want to measure the height of the cliff, we don't usually measure with negative numbers. So if the rock fell from the top to the bottom down 60.09 meters, we can kind of flip that around and say that the height of this is just the reverse. So the height of this cliff must be 60.09 meters, since we measure height, in the positive direction from the bottom up. All right, so you're just going to use kinematics, and we're going to adjust that very slightly. So let's look at one more question so you guys have a chance. This one's a little different. Now we're actually going to throw the rock up in the air. So the rock is now actually going to do this. It's going to go straight up and then straight back down. So we're not just dropping it. It's still in free fall, though. Once it leaves my hand, even though it's traveling upwards, goes to the top and comes down, once it leaves my hand, gravity is the only thing acting on it. So let's go ahead and plug in our values. Well, our initial velocity in this case is actually a positive 8. I'm going to assume that upwards is positive and downwards is negative. So we throw this upwards at positive 8. Final velocity we don't know. Again, that would be the velocity right here just before it hits the water. Probably going to be moving very fast, so we don't know what that is. This is still on Earth, so our acceleration is negative 9.81. Height of that is unknown, and the time is 7 seconds. I'm going to wind up using the same exact equation. If final velocity is what I don't care about, then I know that delta y is VIT plus 1/2 g t squared. And then I can plug in everything I know. Delta y is, well, in this case, we have an initial velocity of 8, and that time was 7. Plus 1/2, I need to recognize that it's negative 9.81 because gravity never pulls things upwards. And this is going to be, whoops, sorry, that was the last problem. This is 7 seconds. And I have to make sure I square that. If I plug all of that in, I'm going to get, let's see, that's 56 plus 1/2 times negative 9.81 times 7 squared is 49. So this gives me negative 184.35 meters. Again, that is actually the displacement. So that's not the distance. That's not this whole pathway. Okay, that would be the distance. That's actually the displacement from here to here. That is what delta y represents. So I can flip that around again to measure it in the more classical sense. And the height of this cliff must be about 184.35 meters. All right, so just understand you can use kinematic equations much in the same way we have been. You just must be very careful. The acceleration, unless you're on another planet, will be negative 9.81. And just recognize that anytime a rock is dropped, you can assume that you know your initial velocity is 0. All right, good luck with that challenge problem. And yeah, good luck.